Welcome back, friends. Yesterday we have started with the classification of systems. In that we have seen what is a linear system and what is a differential equation for a linear system. We have seen that the differential equation for a linear system must be in the form such that its degree for each term must be 1 only. Anything other than 1, then we can say the system is nonlinear. Next classification, what we have to see is time invariant and time variant systems. Time invariant and time variant system. So here the literal meaning of variant is nothing which is changing. Invariant means which is not changing. That's what the meaning of it. So here time invariant system means the system parameters which are not changing with respect to time, or simply we can call constant parameter system. That system should not change. That means if you give the input at any time, the same output we have to see. That means if I give the input now, the same input somewhere else, sometime after that, still we have to get the same kind of output. Then we can call the system is not changing with respect to time. So here we can say in this manner also. Suppose let's say if I take a system, now I have given the input, I am getting the output. After some time I am giving the input, then we have to get the same kind of output. So here if I see, what I am doing is now later, that means I have to give the input now, but instead of that I am giving the input some other time. That means I am delaying the input. Then output is also got to be delayed. So in general we can say time invariant system mathematically can be defined like this. The system produces the output which is a delayed output for a delayed input by the same amount of delay. So I can write like this: time invariant system, time invariant system. It is a system which produces delayed output for delayed input, for delayed input by the same amount of delay. Amount of delay. Okay. Now try to understand. If a system is given to you, if x of t is the input, let's say y of t is the output. Let's say y of t is the output. What if I have delayed the input? That means x of t minus t naught. This is the input what I have given. For this, correspondingly, if the system is time invariant system, then output is also delayed by the same output, same amount of delay. That means we are expecting the output which is nothing but y of t minus t naught. So this kind of output we are expecting. For x of t minus t naught, we are expecting the output which is in the form of y of t minus t naught. If the output is exactly same as this one, then we can say the system is time invariant. Suppose if actual output is not equal to y of t minus t naught, then we can say the system is time variant system. Suppose I will take some examples, you can understand. Let's take the example. Let's say y of t is equal to x of 2t. X of 2t. Is it time variant or time invariant system? It is a time variant system. How, sir? First try to understand the functionality of the system. What do you mean by functionality of the system? If x of t is the input, I am getting output is x of 2t. What is that supposed to mean? x of t, any signal which is given as input, that has to be compressed, or we can say t has to be replaced with 2t. So what the system is doing? Simply in the input, t got to be replaced with 2t. That's what the functionality of the system. Now for this, if I delay the input x of t minus t naught, then what is the actual output? What the system will do? Simply replace t with 2t. Then it is going to be x of 2t minus t naught. X of 2t minus t naught. This is the output what we are going to get actually. But what is the output we are expecting? Expecting output is y of t minus t naught. This is the output we are expecting. If this is the output we are expecting, means that means simply we have to replace t with t minus t naught. Then it is x of 2t, x of 2 of t minus t naught. So that means x of 2t minus 2t naught. This is the output what we are expecting. But instead of that, we are getting this kind of output. So I can say the system is a time variant system. The system is time variant system. Okay, take it. Next example, y of t is equal to 5x of t. Is it a time variant or time invariant system? Let's check it out. So what the system is doing, if anything which is input, that has to be multiplied with 5. That's what the system is doing. So if input is delayed, that is x of t minus t naught, what is the corresponding output? That is actual output, which is nothing but it has to be multiplied with 5. 5 x of t minus t naught. Then what is the expected output? Which is nothing but y of t minus t naught. That means we have to replace t with t minus t naught. Then in this 5 x of t minus t naught. Both are same. So I can say actual output is equal to expected output. I can say time invariant system. It is a time invariant system. Now next, one more example. Y of t is equal to tx of t. Tx of t. If I check whether it is a time variant or a time invariant, you are going to get time variant system it is. How? Let's see. What the system functionality means, what the system is doing for the input. It is simply multiplying the input with a t. So if x of t minus t naught is the input, then what is the actual output? It has to be multiplied with a t. Then it is t x of t minus t naught. This is the actual output. Then what is the expected output? Expected output is y of t minus t naught. That means wherever t is there, that has to be replaced with t minus t naught. Then it is going to be t minus t naught into x of t minus t naught. Both are not same. If both are not same, the system is time variant system. Okay. Next, y of n is equal to root n x of n. So what the system functionality? It is simply multiplying root n to the input. Whatever the input, we have to multiply with root n. That's what the system is doing. So if x of n minus n naught, this is a delayed input in the discrete time case, x of n minus n naught is given, then what is the actual output? Which is root n multiplied with x of n minus n naught. This is what the output we are getting actually. But what is the output we are expecting? Expected output is nothing but y of n minus n naught. That means we have to get root of n minus n naught. Wherever n is there, that has to be replaced with n minus n naught into x of n minus n naught. So both are not equal. So the system is time variant system. The system is time variant system. Now see here, from these three examples, the coefficient of x of t is a 5, which is a constant. The coefficient of x of t is t. The coefficient of x of n is root n. So if the coefficient of x of t is constant, then we can get it is a time invariant. If the coefficient of x is a function of time, then we are going to get time variant system. I hope you understood. Okay, take it. Okay. Now, if let's say y of t is equal to dx of t by dt, dx of t by dt. Is it time invariant or time variant? It is time invariant. But let's see how it is going to be. So what the system is doing, whatever the input is there, that has to be derivated by d by dt. So we have to do the derivation d by dt for the given signal. So if x of t minus t naught is given as the input, then the actual output is nothing but derivative of the input d by dt of x of t minus t naught. That's what the output we are going to get. But what is the expected output? Which is y of t minus t naught. That means wherever you see t, that has to be replaced with the t minus t naught. Then what we are going to get is dx of t minus t naught by d of t minus t naught. Most people think that these two are different. That means expected output and actual output. They may look different, but they are exactly same. How, sir? You might know this. Differentiation of, let's say, t minus 4. It is going to be dt, because differentiation of 4 is nothing but 0. So in a similar manner, differentiation of t minus t naught, because t naught is a constant, so it is nothing but dt. It is nothing but dt. So that's what we are going to be. So this is exactly same as dx of t minus t naught by dt. Both are exactly same. So the system is time invariant system. The system is time invariant system. In the similar manner, if I take running integral, let's say y of t is equal to integral minus infinity to t x of tau d tau. So this input output relation, this system, is it time invariant or time variant? Again I am saying it is a time invariant system. How? See, first we have to understand the functionality of the system. If x of t is given as input, we are getting this is the output. What is the output means here? X of t, it has to be converted into x of tau. That means t has to be replaced with tau and integration from minus infinity to t. That's what it is doing. So what I am doing, if input is x of t minus t naught is given, then what is the output? Actual output. Actual output is nothing but integral minus infinity to t x of tau minus t naught d tau. Tau minus t naught d tau. That's what the actual output we are going to get. Now, what is the expected output? Expected output is nothing but y of t minus t naught. That means wherever t is there, that has to be replaced with t minus t naught. If I see this, it may look minus infinity to t minus t naught x of tau d tau. So by seeing these two integrals, they may look different, but they are exactly same. How they are going to be exactly same? Let's check it out. First, we cannot compare these two integrals directly. Why? The integrand here is x of tau minus t naught. Here it is x of tau. So both are different. If integrands are different, we cannot compare the integrals. Then how we can make them equal? Let tau minus t naught is equal to m. Then what is d tau? Which is dm. Now, if tau value is equal to minus infinity, that implies m is also equal to minus infinity. If tau value is equal to t, then m value is equal to t minus t naught. T minus t naught. So if I replace or if I rewrite this integration, this will look like this. Integral minus infinity to t minus t naught x of m dm. That's what the integration looks like. Now if you have compare them, they are exactly same. Here the only variable is changing. If variable is changes, that integration value does not change. So we can say this is also time invariant system. Time invariant system. So first order differentiation and running integration are nothing but time invariant systems. Okay, take it. Let's say differential equation of a time invariant system. That means, suppose if a differential equation is given to you, we have to say whether it is a time invariant system or not. Okay, so let's see differential equation of time invariant system. So what is the parameter we have to observe in the differential equation so that we can say it is a time invariant system? For that, let's see, I will give you some differential equations and I will tell you which one of them is the time invariant system. From that we can conclude something. Okay, let's see d square y of t by dt square plus 4 dy of t by dt plus y of t is equal to 5x of t. This is the one system. D square y of t by dt square plus 4 dy of t by dt square dt whole square plus y of t plus 5x square t plus 4. This is a one system. Next, d square y of t by dt square plus t square dy of t by dt plus t y of t is equal to t cube x of t. This is another system. Next, d square y of t by dt square plus t square dy of t by dt whole square plus t y of t is equal to x of t plus 4. Okay, now try to understand. I am asking, is it a linear system? Yes, because each term having degree is equal to 1, so it is a linear. This one is a non-linear because this is a non-linear term, this is a non-linear term, this is also non-linear term because degree is not equal to 1. So I can say this is a non-linear. Next, this one is a linear and this one is a non-linear again. But this is not what we have to see. We have to see whether the system is a time invariant or not. Now I am saying this is a linear and time invariant. What about this one? This is a non-linear and time invariant. This is a linear time variant. This is non-linear time variant. See, to check whether it is a time invariant or not, we have to observe the coefficients of each term. The coefficients, if all the coefficients are constants, then we can say the system is a time invariant system. If any one of the coefficient is a function of time, then we can say the system is time variant system. So that's what we have to check. So what are the coefficients? Are they constants, or some of the coefficients are functions of time? So that's what we have to check. So here, let's see. 1, 4, 1, 5. So which are nothing but purely constant. So it is a time invariant system. Now 1, 4, 1, 5, 4. So they are all constants. That's why it's a time invariant. Now if you observe carefully, 1, t square, which is a function of time, t, which is a function of time, t cube, which is a function of time, which makes the system is time variant system. Here also t square, t, and here constant. So these two terms are functions of time. That's why it is going to be time variant system. So this is what we have to check, whether it is a differential equation represent time invariant or time variant system. What we have to check is the coefficients. Are they constants or not? Okay. I am writing that point. A differential equation represent a time invariant system if all the coefficients are constants. That's what the time invariant system. Here, from the linearity and time invariant, we are having a special category of system which is very, very important for us, which is nothing but LTI system, linear time invariant system, LTI system. Now, you have to tell me, that means it has to satisfy both linearity as well as time invariant system. So that means this kind of differential equation which represents the linear time invariant system. So you tell me, for LTI system, what kind of differential equation it is going to be? That means each term having the degree is equal to 1. That is the first condition to make the system linear. And the next condition, each coefficient must be constant, which makes the system time invariant. So these two properties has to be satisfied so that the differential equation represents a linear system and time invariant system. That is LTI system. That means what we have to say? Each term must have degree 1 and all the coefficients must be constants. So these two properties are satisfied, then we can say that system is a LTI system. Okay, take it. Static and dynamic system. Next classification, static and dynamic systems. Static and dynamic systems. Remember, static system is also called as memoryless, or is also called as memoryless. It does not have any memory. And dynamic system having memory. With memory. Now, so before understanding the static system and dynamic system definition, first we have to understand some of the things which are, let's say, y of t, which is nothing but output. For this output, I am giving you three signals, which is x of t, x of t minus 2, x of t plus 2. So we have to decide for this output, this input, is it a present value, past value, or future value? So this is what we have to check. So let's see. For y of t, x of t, suppose if the output is depending on the x of t terms only, then we can say the system is a static system. Or we can say, let's say, x of t, this is the input for this output, that is y of t. We can call this input x of t as a present input for y of t. Why, sir? Because let's say if I want to find out y of 0, then where we have to see the input, which is nothing but x of 0 only. Suppose if I want to find out y of 2, that means at 2 seconds I want the output, then where we have to see the input, that is also nothing but x of 2. So this is also called as a present input. This is called as present input. Next, what about x of t minus 2? What we can call it is, now let's see, if I want the output at y of 2 seconds, that means at 2 seconds I want the output. Where we have to consider the input, that is nothing but x of 0. So the output has to be find out at t is equal to 2 seconds. So where the input we are considering at 0 seconds. So we can call it is past input. Past input. Next, to find out y of t, x of t plus 2. Now you see, y of 0 I want the output. That means at 0 seconds I want the output. So where we have to see the input, which is nothing but 2 seconds. For 0 seconds, 2 seconds is nothing but the future value. So I can say this is nothing but future input. Future input. That's for the future input. Okay. Next, see the definition of static system now. What the definition of static system means? A system is said to be static. Is said to be static if present output depends only on present input. Present input. Then we can call it is a static system. Otherwise, it is a dynamic system. That means present output must depend on present input only. Present output must depend on present input only. Then we can call that is a static system. If it is depending on the past values, then we can say it is a dynamic system because it is having some memory. I hope you understood. Okay, take it. Causal, non-causal system. See, these kind of words we already heard in the signals. That means causal signal, anti-causal signal, non-causal signal. There are three categories of signals, but here we will have only two signals, which are two systems. One is nothing but causal, non-causal system. Now listen carefully. What do you mean by causal system? The definition is like this. If the present output, if the present output is depending on present input and past inputs. Is it clear what I'm trying to say? Suppose if the present output is depending on present input and past inputs, then we can call the system is a causal system. Now, if it is depending on the future inputs, then we can call it is a non-causal system. That is as simple as it. That means it has to see the future inputs. That means we don't know what it is going to be in the future, but still we have to expect the future. Then we have to produce the output now. Then in practical, these kind of systems are not possible. So if suppose somebody is asking which kind of systems are possible, which are nothing but causal systems. Non-causal systems are physically non-realizable. They cannot be realized physically. So only the systems can be realized are nothing but causal systems. So what is the definition of causal system? The present output is depending on present and past, but it should not depend on future inputs. So it should not never or depends on the future inputs. So that is nothing but the causal system. So I can say a system is said to be causal if present output depends on present and past inputs. Understood? Non-causal system is if present output depends on future inputs. Then the system is non-causal system. Practically realizable systems are causal systems. Causal systems only are practically realizable. Non-causal systems are not possible to realize practically. Okay, that's what it is. Okay, take it.